Okay. So imagine this situation where traveling somewhere, I don't know, let's say we're going to the mall, and let's make a graph of the total distance that we've traveled as we're driving. So let's maybe call the horizontal axis time, or t for time. So the time that's elapsed from when we started. And let's call the vertical axis our distance traveled. Okay. So you start out at your home, you haven't gone anywhere else. You have to start out at 0. So we get in the car, we start driving, we start speeding up a little bit. All of a sudden we stop at a stoplight, so here we are stopped. Time's continuing to elapse. We're stopped, but we're not going anyway, so our distance is not increasing. Then we start going again. And we slow down a little bit, and then we speed up, and finally we get where we're going. We stop and hang out there for a while. And now we're going to start going back home. And as we go back home, we're covering more distance, but it's in the direction of back home, so our total distance traveled starts to decrease. Maybe we hit a different stoplight this time. Eventually we get back home. So the whole trip took however long it took, and we traveled out, and then we traveled kind of back in. And so one thing your car can do for you is it can tell you like how fast you're moving at any given time. And the problem I want to ask us right now is just knowing our distance traveled. There's this physics problem that says how fast are you going at any given time. Now you may remember some formula from physics. You may remember, this formula from high school physics that says something like distance, d for distance, equals velocity times time. This formula is totally true, but it's only true if your velocity is constant. But if you're driving in your car, your velocity is not going to be constant. You're going to be speeding up, slowing down, stopping, like so on and so forth. But the only physics formula I know just says, well, if the velocity is constant, then distance is velocity times time, which is also, if I rewrite that, that's like saying that velocity is distance over time. So how can I use this to answer how fast am I going when my velocity could be actually changing? And I want to give you an answer to that question, but I can't do any calculations with this schematic graph. So if you'll let me, I'm going to replace this with something that I can actually write a formula for. And the function that I'm going to use is maybe f of x equals 4 minus x minus 2 squared. I'll explain why. Let's look at this. Here's what the graph looks like. This is centered at x equals 2. When x is equal to 2, y is going to be equal to 4. When x is equal to 0, you're going to get 4 minus 4. When x is equal to 4, you're going to get 4 minus 2 squared, which is 0. And you get this nice, well, there's a negative sign here, so it's a downward facing parabola. So this is like an idealized version of your trip to the mall, where you're just driving straight there and immediately turning around and driving back with no stops. But I can still ask this question, so how fast am I going at any given time? And how can I use this physics formula that velocity is equal to distance over time in order to figure that out? And so let's sharpen up the question a little bit. Let's say how fast am I going when t equals to 1? So how fast am I going, or what's my velocity? And the first thing I want to do here, this is like a hard question to answer. And for argument's sake, let's put some units here. T could be seconds, minutes, hours. Let's just say time is measured in seconds here, and let's say that our distance is measured in feet. So how fast am I going in feet per second? And the first thing that I might want to do is I might want to say, well, I don't know exactly how fast I'm going at the instant t equals 1, but what I can do is I can look at my average velocity. So I can say, on average, how fast am I going? What's my average velocity? From t equals 1 to t equals 2. And if I just look at this interval of 1 second between t equals 1 to t equals 2, and I look at how fast I'm going on average, that can at least give me an estimate for how fast I'm going exactly at t equals 1. So what's an average, or what do I mean by average velocity? What you want is you want to look at your physics equation, which tells me velocity equals distance over time. And what we really mean here is your change in distance over the change in time. And if you're going from 1 to 2, then the change in time, or the length of time you're using, is just 2 minus 1, or 1 second. And then how much distance did you travel? Well, you have to look at the distance traveled after, say, 2 seconds. That's f of 2. That tells you how far you traveled. Minus your distance traveled after 1 second. And so that's your change in distance traveled over your change in velocity. And that's what we call the velocity over that time interval. That's what we call the average velocity. And here I can actually figure it out because I can just plug into the formula. I can plug in 2 into f of x. And I'm going to get 2 minus 2 is 0 squared, so I'm going to get 4 here. And then minus f of 1. Plug in 1, I'm going to get 1 minus 2 is negative 1 squared, gives me 1. So 4 minus 1 is 3. So that's going to be just 1 over 1. And the units are feet divided by seconds, so velocity is in distance over time, so it's feet per second. So that's my average velocity. And one thing that I should point out here is if you look at this point on the graph above t equals 1, the t value is 1, and then f of 1 is equal to 3. And then you look at this point on the graph where t equals 2, and then f of 2 is equal to 4. If you connect those 2 points by a straight line, then you get the yellow line. And this is an example of what we call a secant line. A secant line is any line you take that you get from picking 2 points on the graph. So a secant line for the graph, pick any 2 points you want. For different pairs of points, you'll get different secant lines. But pick any 2 point you want, draw the line between them. That's the secant line. And if I want to find the slope of a line, you know that that slope is the change in y values divided by the change in x values. So what we're seeing here is that the average velocity, AV for average velocity, this is actually equal to the slope of the secant line. So average velocity from 1 to 2 gives you the x coordinates that give you the 2 points. And then the slope of the secant line is going to be that average velocity. And so what I want to do to figure out how fast I'm going exactly at t equals 1, well, maybe I can look at the average velocity on a smaller interval. Maybe I can go from 1 to 1/2 and draw a different secant line. And that average velocity is now on a smaller interval. It's going to look closer and closer to how fast I'm going instantaneously at that point. And then I might take 1 to 1 1/10 or 1 to 1 100th. Take smaller and smaller intervals and calculate that average velocity. And then I want to take a limit of that, and that's going to tell me how fast I'm going at an instant. So let me show you how to do that. So what if instead of going from t equals 1 to t equals 2, I just wanted to find the average velocity from t equals 1 to t equals some unspecified point x. So x would be somewhere around here. You want to make it really, really close to 1, but I just drew it out here so you could see it. So how am I going to do that? Another way to write this would be, if x is bigger than 1, it'd be the interval from 1 to x. Or if x were smaller than 1, it'd be the interval from x to 1. So when you want to find the average velocity, what you always want to do is take the difference between the y values and divide by the difference between your time values. So what I want to look at is f of x minus f of 1, and I know that's equal to 3, divided by x minus 1. So the change in my y values, f of x minus f of 1, divided by the change in the x values, that's x minus 1. So I plug that in, and when I plug in f of x, I'm going to get 4 minus x minus 2 squared minus f of 1, and I know that f of 1 is equal to 3. So I plugged that in before. Divided by x minus 1. And here we do have to do a little bit of algebra. So first, 4 minus 3 is equal to 1. And then x minus 2, well, x minus 2 squared, I can expand that out. So let me continue on over here. I can expand that out. So the 4 minus 3 gives me 1. And then minus x minus 2 squared, that's going to be x squared. And then remember this formula? A plus b squared equals a squared plus 2ab plus b squared. Some people call that foiling it out. So you just use this formula. You get x squared minus 2 times x times 2, so that's minus 4x, and then plus negative 2 squared. And then you're dividing the entire thing by x minus 1. Now if you collect terms, this minus sign distributes out to every single term, so I get 1 minus 4, so that's negative 3. It's going to be my constant term. Here I get minus x squared. Here I get plus 4 times x. And here I get, like I said, 1 minus 4 is minus 3, all divided by x. Minus 1. Okay, so that's what I've got so far. So when x was equal to 2, then this average velocity was 1 foot per second. And if I want to solve this problem for how fast am I going at time equals to 1, all I have to do is plug in x equals 1, right? No problem. Well, actually, it is a problem because I try to plug that in, and then I get this division by 0 issue. So what's going on? We need to investigate a little bit further. So here we can try to factor this. And I'm going to see if I can factor out x minus 1. And what might go on the other side? Well, I want something to multiply by x to give me negative x squared. So I'm going to try putting in negative x there. And let's see, what do I want to add to this? Well, I'm getting negative x squared, and then I'm getting negative 1 times x is giving me plus x. And then I need to get x plus 3x to give me 4x. So I'm going to try x plus 3, because then 3 times x would add together. And I'll see if that works out. I multiply them, I get negative x squared. I get plus x, then plus 3x gives me 4x. Then I multiply these two together, and I get a negative 3. So that's one way you can kind of reason out the factoring, if you like. And then it's still true that you can't plug in x equals negative 1 to this function, but because you can't divide by 0. But it's also true that this function is just equal to negative x plus 3 if you know that x is not equal to negative 1. So the graph of this average velocity function, AV for average velocity, it looks like this. It looks like negative x plus 3 but it's got a hole in it when x is equal to negative 1. So that's what it looks like. So this is the perfect candidate for taking a limit. I can't actually plug in x equals 1 here, excuse me. This has a hole when x is equal to 1, because then 1 minus 1 is 0. So I can't exactly just plug in x equals 1, but what I can do is I can take the limit as x goes to 1. And remember, this was given to me as f of x minus f of 1 divided by x minus 1. And remember, we figured it out using algebra that this is equal to, running out of space a little bit, we figured out using algebra that this is equal to just x minus 1 times minus x plus 3 divided by x minus 1. And So what's this limit going to be? What do the y values get closer and closer to as x gets close to 1? Well, as long as x is not equal to 1, but it's close to it, then you can cancel out this factor. And remember, limits don't care about actually being equal to the point. They only care about close to it. And so you can see from the graph I drew, or you can see from this expression, here you can really plug in 1. That's telling you what the y values are approaching. That's telling you that you're getting that removable discontinuity. So when you plug in 1 here, you're getting -1. Plus 3, you're getting 2. And our units were feet per second. So the eventual answer to the question, how fast am I going? At the point, after 1 second exactly, that's really 2 feet per second. And how can you visualize this? Well, what we've done before we took the limit was we looked at the slope of the secant line from the point 1, 3, from 1 f of 1 to the point x, f of x. So you look at that secant line. So the yellow one was x equals 2, and the orange one, you're starting to get closer. And if you can think of imagining in your mind just moving that x value closer and closer and closer to 1, and eventually what you get is this line that just touches the point t equals 1, f of t equals 3, and has slope equals to 2. So let me quickly put that together. So in physics, we call this instantaneous. Velocity at t equals 1. And what we define it to be is the limit as t goes to 1 of that average velocity. Remember, the average velocity is just change in y values over change in x values. So you look at the average velocity from 1 to x, and you take the limit as x goes to 1, And if that limit exists, that's what we call the instantaneous velocity. And that line through the point, in this case it's 1, 3, so 1 f of 1, and that has the slope given by the instantaneous velocity. In this case, the slope's equal to 2. This is called the tangent line. At the point t equals to 1. So your instantaneous velocity, that's like the slope of your tangent line. That's this line in white. It's a little hard to see, but you can see the yellow, orange, and getting closer and closer to the white line. So how can you find a formula for that tangent line? What you're going to want to do is just use this point slope formula. If you've got a point and a slope, you can always find the equation for the line. You can remember from your pre-calculus class that if you've got a point x1, y1, then the point slope formula says y minus y1 equals slope times x minus x1. So here your point is x equals 1, y equals 3. So I'm going to take y minus 3, because my point was x equals 1, y equals 3, equals my slope, which was 2, times x minus 1. And if you expand that out, bring the 3 to the other side, you're going to get y equals 2 times x. And then minus 2 plus 3, it's going to end up with 2x plus 1. So this is an equation for this tangent line in white. And just another quick terminology. We call that instantaneous velocity. 2 is the derivative of f of x at the point t equals to 1. Well, that's going to be a whole nother video. We'll get there a little bit later, but this is your first example of seeing a derivative of a function. And what I want to emphasize to you is that derivative, it's always going to be the slope of the tangent line. You get that slope of the tangent line always by taking the slope of a secant line and then just taking the limit. Okay, so the concepts here were limits, left-hand limit, right-hand limit, then secant line, then tangent line. And you're using the limit to go from secant line to tangent line. The reason why we care about it in the first place came from physics. It came from, this idea of calculating instantaneous velocity from the position. And there's other applications too. But that's our first introduction to these concepts. Thank you so much for listening. I'll see you later.